Welcome to Demystifying Math. In this lesson, we're going to be discussing vectors. Specifically, we're going to be discussing the scalar multiples of vectors, the unit vector, and dot products. Scalar multiplication is when you multiply a vector by a scalar. Let's say n. What you're going to get is a new vector that has the length n times that of the original vector. You can find the scalar multiple of a vector simply by multiplying the components of the vector by your scalar. So let's say that we had the vector 2, 4. Our scalar is 3, which just means that we're going to multiply the vector 2, 4 by 3. Multiplying the coordinates by 3, you get the new vector 6, 12. Let's go ahead and put these on the coordinate plane. What you should notice is that the two vectors coincide, which means that they're going to form the same angle with the horizontal. The other thing that you should notice is the vector 6, 12 is 3 times the length of vector A. Let's go ahead and verify this by using our distance formula. With the distance formula, we normally have two x coordinates that we subtract, but since our starting point's at 0, 0, looking at vector A, our endpoint is at 2, 4. So 2 minus 0 gives us 2, and 4 minus 0 gives us 4. So we simplified our distance formula down by putting our vectors in component form. So we ended up with 2 square roots of 5 as our length. Now we're doing the same thing to the vector that ends at 6, 12. And when we simplified that distance down, we got 6 square roots of 5, which you should notice is 3 times that of the original vector. So when we multiply by a scalar, if that scalar is greater than 1, it's going to stretch out our vector. If the scalar is between 0 and 1, it's going to shrink our vector. A unit vector is a vector that coincides with the original vector but has a length of 1. Since it coincides with the original vector, it must be a scalar multiple of the original vector. Since it has a length of 1, it must lie on the unit circle. Let's go back to the last example we were looking at. We have vector A that has a length of 2 square roots of 5. What we want to do is find the vector that has a length of 1 that coincides with vector A. So the best way to do that is to just multiply the coordinates of vector A by the reciprocal of its length. Or, in other words, divide the coordinates by 2 square roots of 5. And you're going to get a vector that has a length of 1. Now, let's go ahead and simplify our unit vector coordinates that we got here. So we're going to rationalize the square roots of 5 and then simplify our fractions. So we got the coordinates of the unit vector as square root of 5 over 5, comma 2 square roots of 5 over 5. Let's go ahead and use our distance formula to verify that this vector indeed does have a length of 1. So plugging our coordinates into the distance formula, we're going to square each term first and then add them together and take the square root. Squaring gives us 5 over 25 for the first term and 4 times 5 or 20 over 5 for the second term. Then adding them together we get 25 25ths or 1. Square root of 1 is 1. So it does have a length of 1 and it coincides with the original vector. Remember, in order to be a unit vector, it has to have a length of 1. Okay, let's move on to dot products. To find the dot product of two vectors, all you have to do is multiply the first coordinates together, add it to the product of the second part of the coordinates. And when you do this, you're going to end up with a scalar, not another vector. It's just going to be one number. So let's look at an example. Suppose that we let u equal the vector 3, 5 and v is equal to the vector 6, 4. We're going to take our x coordinates and multiply them together, multiply our y coordinates together, and then add them. So we get 38 as the dot product. Let's do some practices. Let's suppose that p is equal to the vector -2, 3, q is the vector 6, -5, and r is the vector -2, -4. Let's first find p dot q. Again, the dot product, you're going to multiply your x-coordinates together and add it to the product of your y-coordinates. And we get -27. Now, would it be any different if we multiplied q dot p instead of p dot q? Well, not at all, because we're still going to take our x-coordinates and multiply them and add it to our y-coordinates that are multiplied together, and we ended up with exactly the same number. So for dot products, it is commutative. For the third example, we have p dot q dot r. We're going to follow our normal order of operations and find p dot q first and then multiply it by vector r. Now, we know that p dot q is -27 and then r is a vector. So now we're going to be doing a scalar multiple of vector r, which means that we're going to end up with another vector. So -27 times our vector r gives us the new vector 54, 108. The last one says that we're going to take 3 times vector p and multiply it by 4 times vector r. Well, this is a dot product, so we're going to end up with a scalar. So the first thing that we're going to do is take 3 times vector p, and then we're going to take 4 times vector r, and then do a cross product of those, a dot product of those. So you have -6 times -8 plus 9 times -16. And putting those together, we end up with a scalar -96. All right, let's do one more. We want to find q dot q and then compare it to the magnitude of vector q. So looking at q dot q, you're just going to take the 6, -5 and do a dot product with 6, -5. So you have 6 times 6 plus -5 times -5, or 36 plus 25, which gives us 61. Now when we're looking for the magnitude of q, we're going to use our distance formula, because remember, magnitude represents the length. So you have the magnitude of vector q is the square root of the x-coordinate squared plus the y-coordinate squared, which gives us the square root of 61. So what we could say is that the magnitude of the vector squared is equal to the dot product of the vector with itself. Thank you for tuning in. Please contact me if you have any questions.